You have heard the name, you have seen the pictures, the black hole. It is the ultimate boundary, the place where all the laws of physics we know turn into cosmic static. But here is the thing that makes them truly wild. They are the most efficient energy machines in the universe, and we are only just beginning to know the real picture of what goes on inside them. Black holes are created when a star much larger than our Sun, usually 8 times its mass or more, reaches the end of its life. The star runs out of nuclear fuel, and gravity, which has been pulling the star together its entire existence, finally wins the fight. The core collapses rapidly, compressing down until the object is so dense that nothing can resist its gravity. The size of the Sun, for example, would have to shrink down to about 1 mile across to turn into a black hole. If the Earth were to suffer the same fate, it would need to compress to the size of a sugar cube. The collapse is cataclysmic, resulting in a supernova explosion. But what is left behind is not a surface. It is a region of space-time defined by pure, warped gravity. This region is only described by 2 numbers, its mass and its spin. If you were falling toward this collapsing star, the first and most important boundary you would meet is the event horizon. What exactly is the event horizon? Simply put, it is the edge where the escape velocity is equal to the speed of light. Escape velocity is the speed you need to travel to escape the gravitational pull of an object. For Earth, escape velocity is about 8 miles per second. For the Sun, it is much faster. But for a black hole, the gravity is so tremendously powerful just outside this line that you would need to move faster than the universe's absolute speed limit, the speed of light, to get out. Since nothing can travel faster than light, once you pass the event horizon, you are trapped forever. The location of this border is defined by the mass of the black hole. The larger the mass, the larger the radius of the event horizon. We see this concept in the largest black holes, known as supermassive black holes, which are millions or even billions of times the mass of the Sun. They live at the center of nearly every big galaxy, including our own Milky Way. We might assume that the event horizon is a physical, hard surface, but it is not. It is simply a boundary in space-time. Everything outside this boundary, including the surrounding universe, cannot communicate with the region inside it. Light that falls in cannot escape. This is the true definition of a black hole, an object that cuts itself off from the rest of the cosmos. This boundary forces us to confront some bizarre realities, especially when we consider 2 different viewpoints, that of an outside observer watching something fall in and that of the person doing the falling. This is where time truly begins to break, separating what the outside world perceives from what the falling observer experiences. The event horizon changes everything you know about time and space, especially due to a concept known as time dilation near the horizon. Time dilation refers to the slowing of time in a gravitational field. To an observer far away, perhaps floating safely outside the gravitational influence of the black hole, the passage of time for an object approaching the event horizon appears to slow down dramatically. This slowing of time is a direct prediction of Einstein's theory of relativity. Imagine you are watching a spaceship fly toward a black hole. As the ship gets closer and closer to the event horizon, its clock seems to tick slower and slower from your viewpoint. The external observer would see time on that falling object slow to a stop exactly as it reaches the event horizon. The ship's light would become incredibly redshifted, stretched to longer and longer wavelengths due to the extreme gravity, causing the ship to appear redder and dimmer until finally its light fades entirely just before crossing the threshold. Because of this bizarre effect, observers outside the black hole might say that anything falling in never actually crosses the border. They see it frozen, their time having stopped right at the edge. However, the reality for the unfortunate passenger is totally different. This brings us to what an outside observer sees versus a falling observer. For the person or astronaut falling toward the event horizon, their experience of time remains normal. Inside the spaceship, the clock ticks normally, and the astronaut feels perfectly fine as they cross the point of no return. The immense gravity only becomes noticeable after crossing the event horizon and heading toward the center. The boundary itself does not feel like a brick wall. They would simply pass through it, continuing their rapid descent toward the center. This contradiction that one person sees time stop while the other feels nothing unusual highlights how general relativity profoundly distorts reality in the immediate vicinity of the black hole. In the 2014 movie Interstellar, this time warping effect was displayed graphically when comparing the aging of Murph, Cooper's daughter, to Matthew McConaughey, illustrating how time slows down near a black hole. Now, imagine what happens after crossing the event horizon. The light from the surrounding universe is bent and focused by the gravity, leading to strange visual effects. The light rays reflecting off material near the black hole get bent and distorted, turning the black hole into a powerful gravitational lens. An outside observer looking at the accreting gas might even see the back of the disk bent around the black hole, appearing above it. But the fate of the falling object deep inside the black hole is far more severe, governed by a dramatic stretching known as spaghettification. Let's see what gravity actually does to your body once you are inside the region of no escape. The term spaghettification refers to the extreme tidal forces experienced by an object as it falls deeper into the black hole's gravity. Tidal forces are the difference in gravitational pull across an object. You can think of it like this. The side of any object nearer to the source of gravity feels a stronger pull than the side farther away. Near a small black hole, like one left over from a single dead star, this difference is extreme. The gravitational pull on the side of your body closer to the center would be immensely stronger than the pull on your feet farther away. This gravity difference would literally stretch the body vertically while squeezing it horizontally, pulling it into a long, thin strand like spaghetti. This ripping happens long before the object reaches the center, meaning the falling observer would be ripped apart at the atomic level. This force of gravity increases rapidly as you approach the core of the black hole. The sheer density of the compact object at the core is the root of the problem. For a supermassive black hole, which can be millions of miles across the event horizon, is so large that the gravitational gradient is much gentler. You would cross the event horizon unaware, and the stretching effects might only appear much later, closer to the center. So, while one might feel nothing unusual crossing the boundary of a supermassive black hole, the end result is the same: destruction via massive gravitational shear. Regardless of whether the object is gently stretched or violently shredded, every object that crosses the event horizon is headed toward the ultimate destination, the singularity. The singularity is where general relativity predicts the mass of the black hole resides, an infinitely dense point at the very center. This is the ultimate endpoint of gravitational collapse. When a massive star collapses, all of its material is compressed into this single point of infinite density. This location is where physics breaks down. In standard general relativity, the presence of the singularity is certain, but physicists doubt that this description is really true because when the equations of physics are run to describe the matter at this infinite density, the math yields infinity. Infinity is considered an unsatisfactory answer in science. This breakdown suggests that the current laws of physics are incomplete and cannot fully describe the conditions at the black hole's center. The singularity is not just an impossibly dense point in space, its theoretical nature is stranger still. According to maps of the black hole called Penrose diagrams, the sheer distortion of space and time is so extreme that their roles switch. The singularity becomes not a place in space, but a moment in time specifically, the end of time for anything that falls in. This profound change in how reality is structured forces us to rethink everything about space and time themselves. Because our physics cannot handle the extreme conditions of the singularity, scientists are attempting to combine the theory of general relativity with quantum theory. Many theoretical physicists suspect that quantum effects may soften the singularity, meaning the point of infinite density might not actually exist if a proper theory of quantum gravity could describe it. Finding a way to unify these two great pillars of modern physics is often called the holy grail of theoretical physics, and black holes are forcing us to confront the need for this deeper theory of reality. This junction of general relativity and quantum theory led Stephen Hawking to propose one of the most puzzling questions in modern science: the information paradox. General relativity says that nothing inside the event horizon can affect the outside world. A black hole, if it were only governed by classical gravity, is a cold, dead object. However, Hawking applied quantum theory to the boundary of the event horizon and found that black holes actually radiate energy. This is not light escaping the black hole, but particles being produced near the horizon due to quantum mechanics. The laws of quantum mechanics allow pairs of particles to momentarily appear and disappear, or be created and annihilated, even in seemingly empty space. Near the event horizon, sometimes one particle of the pair is created inside the border while its partner is outside. The partner outside can then escape into the universe as Hawking radiation. Because the escaping particle carries energy away, that energy must come from the black hole itself. This means black holes are not eternal prisons. They slowly shrink over time and will eventually evaporate and disappear completely. The paradox arises when considering where the information went. Information in physics refers to all the data about the composition and arrangement of matter. The most fundamental laws of nature state that information must be conserved, meaning it cannot be destroyed. If you take a complex object like a book and burn it, in principle, every piece of light and ash could be collected to reconstruct the original object, proving information conservation. But if you throw that complex object into a black hole, and the black hole eventually disappears, leaving behind only featureless Hawking radiation, it seems that information has been permanently destroyed. This conflict between the conservation of information and the apparent erasure by black holes is the information paradox. It was a major shock to physicists when proposed in 1974. The current general view is that black holes do not erase information. This suggests that somehow the information about everything that fell in is imprinted in the radiation that escapes, implying that space and time themselves may not be fundamental, but rather are emergent space-time. This idea forces us to question if the origin of the universe itself had a beginning, since we must first fully understand what space and time are. When talking about black holes, the divide between what we know versus what we don't is sharp and clear. We know much about the external universe defined by general relativity, but almost nothing about the interior realm of quantum gravity. What we do know, we are confident in the nature of the event horizon as the boundary of no return, where time slows down to a stop for outside observers. We know that matter falling toward the black hole releases tremendous energy in the surrounding accretion disk. The gravity of the black hole powers the disk by converting the material's gravitational potential energy into heat and light, heating the material to millions of degrees before it crosses the boundary. This energy release from infalling material makes black holes the most efficient energy converters known. The core process of accretion converts up to 40% of the infalling matter's mass into radiation, compared to less than 1% converted by stellar fusion. This efficiency explains why feeding black holes become active galactic nuclei, AGN, and quasars, which are the brightest continuous sources of light in the universe, temporarily outshining entire galaxies. We know that black holes can spin, and when they do, they distort spacetime itself. This rotational effect is called frame dragging, literally pulling the fabric of space and time into a whirling motion around the black hole. This spin is a key property of the black hole itself. This rotation is thought to help drive the most powerful features associated with active black holes, astrophysical jets. These jets are tightly focused beams of matter and radiation ejected away from the poles of the black hole at near the speed of light. These jets are not made of material that fell into the black hole, but rather are accelerated particles drawn from the surrounding accretion disk. One leading idea is that the black hole's spin drags and twists the magnetic fields generated by the charge particles in the accretion disk, funneling the energy and plasma out along the poles. This process extracts rotational energy from the black hole itself to power the jets. These jets are incredibly powerful, stretching across millions of light years, and they act like cosmic sculptors, regulating the growth of the galaxy by heating and pushing gas away, preventing too many stars from forming. Understanding the dynamics of this accretion disk near the horizon is the best way to determine the black hole's fundamental properties, especially its rotational speed. We just looked at how energy is generated outside the black hole, but the unknown aspects remain profound. What we don't know, the inside, we do not know the physical nature of the singularity. We cannot truly answer what happens to all that matter that fell in, because our classical laws fail at infinite density, yielding infinity. This ignorance at the center forces us to search for a theory of quantum gravity. Furthermore, we do not fully understand the formation mechanism of supermassive black holes. They seem to have existed remarkably early in the universe, already massively large only hundreds of millions of years after the Big Bang, suggesting they must have grown extremely quickly. Ideas include mergers of smaller black holes or the direct collapse of huge gas clouds. The fact that black holes are invisible means we rely almost entirely on indirect observation to confirm their existence and measure their properties. How scientists study black holes indirectly by observing their powerful influence on their surroundings. 1. Observing stellar orbits, measuring mass. The best evidence for a black hole's existence comes from watching objects orbit around an unseen center of gravity. Astronomers track the motion of stars near the center of a galaxy to determine the mass of the compact object at the core. This technique is analogous to Kepler determining the mass of the Sun by observing planetary orbits centuries ago, even if the central object were dark. In our own Milky Way, tracking the paths of stars near the central radio source Sagittarius A revealed that they orbit a point with 4 million solar masses packed into a small area. This proved the existence of the supermassive black hole at our galaxy's core. To concentrate that much mass into such a small volume, excluding other options like dark clusters of rocks or neutron stars, the object must be a black hole according to general relativity. 2. Analyzing accretion disk emissions, measuring efficiency and spin. When gas and dust are drawn toward a black hole, they form an accretion disk, which heats up due to friction and turbulence, radiating energy across the electromagnetic spectrum. This light, especially in the X-ray range, allows us to study the black hole without seeing it. The rapid flickering or variability of the X-rays emitted from the innermost disk confirms that the light source must be extremely compact, much smaller than an ordinary star. If these X-rays change brightness hundreds of times per second, the source itself cannot be larger than the distance light travels in that short time span. The sheer power coming from a tiny region is the observational proof of size. The brightness difference between accreting neutron stars and accreting black holes also supports the event horizon. Black holes swallow the infalling energy, making them up to 100 times dimmer than accreting neutron stars, which radiate that energy upon impact with their surface. Scientists can also estimate the black hole's spin rate by observing the distortion of the X-ray light emitted from iron atoms near the core. Extreme gravity near the horizon causes this light to be greatly redshifted and Doppler shifted, creating a smeared-out appearance. A greater distortion means the light originated closer to the black hole, which is only possible if the black hole is spinning rapidly, pulling the boundary of the stable orbit inward. The process of finding black holes is one of the greatest triumphs of modern science, combining physics and astronomy. For stellar mass black holes, the threshold is clear. If a dark compact object exceeds 3 times the mass of the Sun, it must be a black hole, since anything smaller would be a neutron star. When searching for stellar mass black holes in binary systems, where the black hole orbits a visible companion star, astronomers must wait for the radiation to stop. When the black hole is actively feeding, the light from its accretion disk is so bright it outshines the companion star. Astronomers wait for the X-rays to turn off before they can measure the companion star's orbit, and thus accurately calculate the mass of the invisible object. Once the mass is confirmed to be above the 3 solar mass limit, the object is dynamically confirmed as a black hole. This dynamic confirmation is what scientists rely on when they study strong field relativity effects that are only visible when extremely close to the event horizon and that have no counterpart in Newtonian physics. 3. Detecting gravitational waves, observing dynamics. The universe's biggest crashes involve black holes. The most powerful confirmation of their dynamics comes from listening to the fabric of space-time itself. When 2 black holes collide, they produce gravitational waves, ripples in space-time that carry massive amounts of energy. The merger of 2 black holes converts the mass equivalent of 3 suns into pure gravitational radiation in less than a second. These events are so energetic that the power output briefly exceeds the total luminosity of all the stars in the universe combined. Detecting these waves allows scientists to map the final, violent moments of black holes colliding. The Laser Interferometer Gravitational Wave Observatory, LIGO, co-founded by Kip Thorne, was designed to detect this stretching and squeezing of space. Gravitational waves are different from the electromagnetic waves traditionally used in astronomy because they are oscillations of the fabric of space-time itself, rather than electric and magnetic fields. These waves travel through matter unscathed, unlike light, which can be easily absorbed or scattered by gas and dust. This technique of gravitational wave astronomy provides a totally new window onto the universe, allowing us to observe events that are otherwise invisible and silent. LIGO's detection of colliding black holes confirmed the final, turbulent dance of these objects, showing that the predictions of general relativity hold true, even in these extreme conditions. The massive merger detected in 2015 produced a chirp sound when translated into audible frequencies. Future plans include the Laser Interferometer Space Antenna, LISA, which will use spacecraft millions of kilometers apart to track gravitational waves from even larger events, such as supermassive black holes merging at the centers of galaxies. Black holes are the engines of the universe, shaping galaxies through their powerful energy output. By learning to read the scattered signs they leave behind the spinning stars, the flickering light, and the ripples in space-time, we continue to map the ultimate frontiers of physics. We have looked closely at the complex, almost paradoxical physics of black holes. Remember the key facts that define these strange objects. The event horizon is the one-way door defined by gravity so strong that nothing, not even light, can reach the escape velocity needed to get out. The size of this border scales directly with the mass of the object inside. The concepts of time and distance break down at this edge. To an outsider, time for a falling object slows down and stops right at the horizon in an effect called time dilation. But the person falling crosses the boundary without feeling anything unusual. Deep inside, tidal forces violently stretch anything toward the center, a process nicknamed spaghettification. All mass eventually heads toward the singularity, the point of infinite density where all of our current physical laws fail. The conflict between gravity and quantum theory produces the information paradox, the theoretical problem of how black holes seemingly destroy information, violating one of physics' most fundamental laws. This suggests that space and time itself might be emergent, built from something more fundamental. We cannot see black holes directly, but scientists study black holes indirectly by observing the incredible effects they have on their surroundings. We measure their mass by tracking the rapid orbits of nearby stars. We measure their properties, their spin, and their compactness by observing the rapid flickering and distorted light of the matter-rich accretion disks that surround them. Finally, we observe their final, violent moments by listening for the gravitational waves they emit when they merge. Black holes are indeed the ultimate cosmic monsters, representing the most extreme physical phenomena known to science. They defy our logic and push the limits of our understanding, driving the search for a unified theory of reality. But for all their terrifying power and efficiency, they are often quiet, distant members of the cosmic neighborhood. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. They are simply part of a much larger, more violent and chaotic universe. If you thought black holes were the biggest problem out there, you need to see what happens when that energy is suddenly focused and aimed across the cosmos. Click here to learn why the real danger is not a black hole.